Hello all. In this lecture, I am going to start with field effect transistor, that is FET. Okay. You know the FETs are called as unipolar device or majority carrier device because the current is due to either electrons or holes. And also the carrier movement is due to మళ్ళీ స్టార్ట్ చేయనండి. Yeah. Hello all. In this lecture, I am going to start with the field effect transistor, that is FET. You know FET also called as majority carrier device or unipolar device because the carrier movement is due to, means the current is due to either electrons or holes. And also the carrier movement in case of FET is due to drift. Whereas in BJT, I think I already told, the carrier movement is due to two types of mechanism, that is drift mechanism and diffusion mechanism, right? Yeah. But in case of FET, the carrier movement is due to only one type of mechanism, that is drift mechanism. I think I already defined what is drift and what is diffusion in my chapter 2, right? See here, coming to the classification of the FET. Coming to the classification of the FET, see here the FETs are two types. So basically the FETs are two types actually. One is MOSFET, another one is JFET. MOSFET means metal oxide semiconductor field effect transistor. JFET means junction field effect transistor. Here the very interesting point is, you know the MOSFET is combination of the three materials, metal, oxide, semiconductor. But junction field effect transistor is a pure semiconductor structure. Okay. Next, coming to the classification, further classification of MOSFET here. You know the MOSFET again can be classified into two types. One is E-MOSFET, enhancement MOSFET, and another one is depletion MOSFET. That is, simply we can represent as D-MOSFET. Again, this E-MOSFET can be classified into two types based on the doping actually. That is N-channel and P-channel. Similarly, depletion MOSFET also can be classified into two types, N-channel and P-channel. Yeah. This is the classification of MOSFET. Coming to the JFET actually, JFET also can be classified into two types. One is N-channel, another one is P-channel. Right? Yeah. These are the different classification of FETs. Okay. Yeah. Write down this. Write in the notes. Write down FET heading. It is also called as unipolar device or majority carrier device. Unipolar device or majority carrier device because carrier movement is due to, because current is due to either electrons or holes, and carrier movement is due to drift mechanism. Yeah, and copy this one. Yeah, completed. Now, Here I am going to start with MOSFET. Actually, in our gate syllabus, only MOSFET is there. JFET is not there, but I will also discuss JFET also. But first, I will start with MOSFET. Yeah. So in MOSFET, I think I already told now two classifications. One is enhancement and another one is depletion, right? So first, I will start with eMOSFET. eMOSFET N channel. Yeah. Next heading eMOSFET N channel, and one more heading here, construction. Yeah. So here to construct N channel enhancement MOSFET, first consider lightly doped PTF semiconductor material here. Lightly doped PTF semiconductor material. This lightly doped PTF semiconductor material acts as a substrate or bulk, and it can provide mechanical support. And the next step is see, create two heavily doped N plus regions into a substrate by using a diffusion process. Okay, these heavily doped N plus regions can act as a source as well as drain. Okay, this is our step 2, and step 3 is see, a oxide layer is formed. A oxide layer is formed over a substrate. By using what process? Oxidation process. Then it can act as a insulator or dielectric or masking. And what is masking here? Masking is nothing but selective portion of doping. Selective portion of doping is called as masking. This is our step 3. And next one, contact cuts. Yeah, how to make contact cuts actually here? See, contact cuts are made on source as well as drain by using photolithography and etching process. Actually, photolithography is nothing but a light is instead on a semiconductor material wherever you want actually. Okay, that instant light actually can react with this oxide actually, and we can easily remove this oxide from the selective portion. That means after instant light actually, okay, this oxide layer becomes softer. So once the oxide layer becomes softer, we can easily remove by using etching process, right? Yeah, next one, after making contact cuts actually, what is the next step? A metal is deposited into a contact cuts. Metal is deposited into a contact cuts by using what process actually? Metallization process. Okay, and it can provide a physical connection to source as well as drain. And next one, another metal is deposited on an oxide layer by using chemical vapor decomposition method. Okay, this can act as a gate. Okay, and one more point here, in modern MOSFETs, instead of metal, a heavily doped polysilicon is used as a gate instead of metal, because this heavily doped polysilicon offers less resistance. Less resistance means it offers high conductivity. Okay, and this is what actually construction of N channel eMOSFET. Similarly, if you want to construct P channel eMOSFET, then you can consider exactly opposite. Means here what is the substrate in case of N channel? P, right? Yeah, in case of p channel, you know the substrate should be N. Also, what are the regions here? This is P plus, this is P plus, like that. You have to take, right? Yeah, copy here. Write out the points first. Construction, write out. Consider a lightly doped p-type semiconductor material, a lightly doped p-type semiconductor material, which can act as a substrate or bulk, and it can provide mechanical support. It can provide mechanical support. Next point. Two heavily doped N plus regions are created. Two heavily doped N plus regions are created into a substrate by using impurity diffusion process. Impurity diffusion process. Yeah. Therefore, these heavily doped N plus regions acts as a source as well as drain. Source as well as drain. Yeah. Copy na? Yeah. Next point. A oxide layer is formed over a substrate. Oxide layer is formed over a substrate by using oxidation process. By using oxidation process. Oxidation process. This oxide layer can act as a insulator or dielectric or masking. Yeah, underline insulator, dielectric or masking. Yeah, next point. Masking is the selective portion of doping. Masking is the selective portion of doping. Yeah. Next point. Contact cuts are made on source and drain. By using photolithography and etching process. Yeah, next point. A metal is deposited into a contact cuts. By using metallization process. And it can provide physical connection to source and drain. Yeah. Next point. Another metal is deposited on a oxide layer by using chemical vapor decomposition method. Chemical vapor decomposition method. Which can act as a gate. Right. Next one, note. In modern MOS device, comma, instead of metal, a heavily doped polysilicon is used as a gate. Is used as a gate. Is used as a gate because it offers less resistance. It offers less resistance. Yeah. Yeah, copy this one. Copy the structure. Yeah, after completion of construction, next here start working or operation. And next stop is working. Right. Yeah, Suno here. See here, to explain the complete operation of the MOSFET, okay. So he required two voltages actually. One is VGS. VGS means the voltage between gate and source. Okay, and another one is VDS. VDS is nothing but the voltage between drain and source. Okay, here what is the use of the VGS here? The purpose of the VGS is to create the channel. I think I already told we have two MOSFETs, right? One is enhancement MOSFET, another one is depletion MOSFET, right? You know, the basic difference between enhancement and depletion is, in case of enhancement, the channel is absent. In case of depletion, the channel is present. That means here we have to create the channel in case of enhancement. See, here, there is no channel, right? We have to create the channel. Yeah, how to create the channel? With help of VGS. Okay, you know, for N channel, the VGS should be positive. For P channel, whatever the VGS here, negative. Okay, next coming to VDS. Yeah, what is the use of this VDS? You know, this is used to enable the movement of the charge carrier from source to drain. See, once the channel is created, then how to move the charge carrier from source to drain, right? With help of VDS. Okay, for N channel, this VDS should be positive. For P channel, the VDS should be negative. Right. Yeah, copy here, write out. Write in your notes. Heading, working. Yeah. The complete operation of the MOSFET can be determined by two voltages. One is VGS and another one is VDS. Okay. Yeah. First heading VGS. It is used to create the channel. Yeah. For N channel, VGS is positive. For P channel, VGS is negative. Yeah, next one, VDS. It is used To enable the movement of the charge carrier, to enable the movement of charge carrier from source to drain. From source to drain. Yeah, for N channel, VDS is positive. VDS is positive. For P channel, VDS is negative. VDS is negative. Right. Yeah. Next. Next heading. Case 1. VDS is varying. And VDS is constant. Yeah. Just now I told now. See, the complete operation of the MOSFET can be determined by two voltages, right? One is VGS, another one is VDS. Now, here I am explaining the working of the MOSFET, okay, in two cases actually. The first case I start with VGS is varying and the VDS should be constant, right? See what happens. See, to explain this, again I am redrawing the MOSFET here. Yeah, copy here. VGS is varying and VDS is constant, right? Yeah, copy. Copy this diagram. Copy, right? Yeah, don't copy these two diagrams, just wait. Yeah. Yeah, first, what is case 1 here? VGS is varying, right? Now I start with like this. So when VGS is 0 here, when VGS is 0, because it is varying, right? It should be constant. So means we are applying some VGS here, but that should be constant here. We are varying VGS. So VGS is 0, okay? So when VGS is 0, actually what about the current IDS here? The current IDS also 0. Why current IDS also 0? Because here the channel is not created between source and drain. I told what is the use of the VGS? To create the channel. When VGS is 0 means there is no channel in between source and drain. Then what about the current IDS value here? 0. Okay. Similarly, when VGS is increases. VGS is increases. Actually, what is the VGS? Here it is N channel, right? Substrate P type means it is an N channel. So here VGS is increases, that means it is positive, right? See, when VGS is positive, you know, what about the metal become actually? The metal become positive. Metal become positive. See, metal become positive means, and also it can polarize the oxide layer, right? It can polarize the oxide layer. It can polarize the oxide layer means it can separate the negative charge as well as positive charge. You know, oxide layer will contain two charges, actually means two ions. One is positive ion, another one is negative ions. Both are immobile. Okay. See, whenever the VGS is positive, then this metal become positive. Then it can polarize the oxide layer. That means it can separate the negative charge as well as positive charge like this. Okay, see, this positive charge within an oxide layer can repel the holes. Actually, what is this material? P type, right? P type means it contains what? Acceptor along with hole, acceptor along with hole, acceptor along with hole, right? You know, this positive charge can repel these holes, can repel these holes between the region source and drain. Then these holes are depleted from this region, and it can form a depletion region, region. It can form a depletion region. Okay. Next, see, when VGS is increases further, actually, then what happen? See, when VGS is increases further, what happen actually? You know, the more charge is present on metal actually, that means the positive charge within an oxide layer can become strong. The positive charge within an oxide layer can become strong, and it will start attracting the minority carriers from the substrate. See, what is our substrate? P type. What are the minority carriers in the substrate? Electrons. And it can start attracting the minority carriers, that is electrons, from the substrate, and also majority carriers from the source and drain. Actually. Okay, due to which this region is fully occupied with electrons. Okay, as a result, this region can act as a inversion region, or channel or N region. Actually, why it is named as inversion region? Actually, see, before applying the VGS, actually, what is the material? P type. After applying some voltage, actually, I think this material will become a N type. That means inversion is happening here. Am I correct or not? What is mean by inversion? Inversion is nothing but it's a process of converting of P type to N type. That's why it is named as inversion layer or inversion region, or this is also called as what actually? N region, or it is also called as channel. Okay. Now here I can define a threshold voltage here. Now I can define a threshold voltage that is represented with VTH. Threshold voltage. What is the threshold voltage actually? Threshold voltage is nothing but the applied voltage at which, okay, the electron concentration in the channel. The electron concentration in the channel is equal to hole concentration in the substrate. Yeah, that voltage is called as threshold voltage. So where, okay, the voltage at which where electron concentration should be equal to hole concentration, that voltage we are going to be defined as a threshold voltage. Okay. And next one, see, for N channel actually, this threshold voltage is what? Positive, because VGS is positive. Threshold voltage is nothing but VGS only. That's why VTH is positive. For P channel, what about the VTH here? The VTH is negative. Yeah. And the last point here, actually, see, when VGS is increases further here, that means VGS is increases further means this VGS should be greater than VTH. This VGS is increases Further means VGS is greater than VTH. See, when VGS is greater than VTH, what happen? When VGS is greater than VTH, what happen actually? You know, the electron concentration in the channel increases. Electron concentration in the channel is increases. Okay, and also conductivity of the channel is increases. Conductivity increases means what is the channel resistance? Decreases. Then what is the current IDS? Increases. Current IDS is increases. Okay, now I am going to plot transfer characteristics here. Here I am going to plot transfer characteristics. See, the transfer characteristics are drawn between IDS versus VGS. IDS versus VGS by keeping which one is constant here? VDS is constant. VDS is constant. Okay. Now, when VGS is zero, okay, what about the current IDS? Zero, because the channel is not created. Getting or not? So here when VGS is increases up to some point means at what voltage? Threshold voltage, right? So what is the current IDS value? Still zero, because the channel is not completely formed. Where the channel is completely formed? At threshold voltage, right? See, when VGS is increases further, then what is the current IDS here? The current IDS is suddenly increases because the channel is created. Channel conductivity is increases, electron concentration is increases, so the current is suddenly increases, right? This is the transfer characteristics for which channel? N channel. Okay, this is about case 1. Yeah, write down. Write down. When VGS is zero, current IDS is zero. Current IDS is zero because channel is not created between source and drain. Channel is not created between source and drain. Right. Next point. When VGS is increases, that means in bracket positive. Then metal become positive. And also it can polarize the oxide layer. That is, it can separate the positive charge and negative charge. Yeah, next point. The positive charge within an oxide layer, can repel the holes between the region source and drain. Between the region source and drain. Due to which holes are depleted from the region. And it can act as a depletion region. Yeah, underline depletion region. Yeah, copy this figure. Yeah, copied. Yeah, next point. Next point. When VGS is increases further, then the positive charge within an oxide layer can become strong. The positive charge within an oxide layer can become strong. And it will start attracting minority carriers from the substrate and majority carriers from the source and drain. Due to which the region fully occupied with electrons. Next one. As a result, this region acts as a inversion region or channel or N region. You underline inversion region, channel or N region. Underline. Yeah. Next point. The applied voltage at which applied voltage means gate voltage. The applied voltage at which electron concentration in the channel is equal to whole concentration in the substrate. Whole concentration in the substrate is called as threshold voltage. Now in bracket VTH. Yeah. Next, for N channel, this VTH is positive. For P channel, VTH is negative. Yeah. Copy this diagram. This one. Yeah. Copy it? Yeah. Yeah, next point. See, when VGS is greater than V threshold, then electron concentration in the channel is increases. Conductivity of the channel is increases. And channel resistance is decreases. And current IDS is increases. Right? Current IDS is increases. Yeah. Next, heading transfer characteristics. Yeah. Copy here. This one. Also copy this one. This is case 3. VGS is greater than V threshold. Copy this diagram. Also copy this diagram. Transfer characteristics. Copied, right? Yeah. See, this is the transfer characteristics for N channel, right? Yeah. See, for P channel, how the transfer characteristics are looking. See here. For P channel, just now I told V threshold voltage is negative, right? Means VGS is negative. VGS is negative. This is negative axis. See, the characteristics are like this. This VTH is negative. Yeah, copy. This is for P channel. Copy. Copied now? Yeah. Thank you. I think in the next lecture I will explain case 2. With that, the total MOSFET operation is completed, right? Yeah.